presentation, but then, of course, aside more offline. Okay, thanks again. Let's go to the third paper on comparing stochastic and ray-tracing datasets in machine learning for wireless communication with my just graduated PhD student, João.
Thank you. Wow. It's great to see a full room with many familiar faces already. Hopefully, people that are revolted with stochastic datasets. We'll see. Well, let me take this out, otherwise NVIDIA is going to complain. Oh yeah, it's cutting a bit on the side. Well. So my name is João. I'm the first author of this paper comparing stochastic and ray tracing datasets in machine learning for wireless applications. And this was a joint work with my previous and loved PhD group, Wireless Intelligence Lab in Arizona State University, and with Interdigital, with Akshay and Shahab that are also here. Actually, all my co-authors are here, so worst case scenario, we can us four discuss this at the end, but hopefully people have some questions and we can interact with them. And as a subtitle that I like, are stochastic datasets all we need? So let me start by setting the stage. What is the status quo? What is the problem we are trying to solve? Currently, stochastic channel models like 3GPP, TDL, CDL, UMA are widely used for more than 10 years, almost 20. And why, when we have so many more realistic channel models? There are quite a few good reasons. The first one is that they are standardized, and in wireless, we like and trust our standards. So just because of that, it already makes it more likely to be used, but they are also reproducible and scalable. So you can set your seeds, you can generate as much data as you want. Also, they were sufficient at the time, and even today, they are still sufficient in many applications. But that boundary of what makes them sufficient is starting to get a bit blurred, especially with the new machine learning applications we are considering, beam management, localization, the digital twin sort of problems that start needing more site-specific propagation models and models that are more spatially consistent, temporal consistency. Now the problem and the cost of ignoring this would be to use unrealistic data and to eventually end up working on the wrong problems and having solutions that don't scale to the real world. Now, ideally, we would have these real-world data that we could fine-tune on, train on, but we don't. But we do have something pretty close, which is ray tracing. And in this presentation, we're going to use it as a proxy for the real world. And there's plenty of research that if you do match your materials, it can get close. So in this presentation, the idea is to understand when each of these types of data sets should be used and how you should use them for making sure things are transferable to the real world. So we're going to answer two questions. Does stochastic provide realistic performance expectations? And if not, and then we are going to need ray tracing, then is stochastic completely useless? Or can it be used for pre-training? These are the two that we're going to focus on, and this is essentially the outline of this presentation. A quick overview of channel models first. Then, based on those channel models, we're going to see that many have certain assumptions, and we're going to choose tasks where those assumptions are sufficient to model the task, and some where they are not. And then train models on those tasks, and based on the model's outcomes, understand if stochastic is all we need, essentially, or if it is also useful, if it's not all we need. So to start, channel models can be laid out in a continuum of determinism. In the beginning, you have your white noise, your Rayleigh. Then you start having your CDLs, TDLs, where 3GPP started to standardize them. And they start to use the geometric channel equations. And all the way to the end, we have the map-based, more of the ray tracing kind. And what is key to understand here, especially on the more realistic models, is that they all use the geometric channel equation. And this equation has many parameters, it has a number of paths, path gains, angles of arrival and departure, delays, phases. And how these parameters are modeled is going to determine the consistency of your model. And the more deterministic your model is, closer to ray tracing, the more these parameters are derived directly from the scene in a deterministic way, like with the equation, for example, modeling reflections. So, like I said, these will impact consistency. In terms of consistency, which will be our bridge to the tasks, consistency can be measured across a few axes. Time, of course, frequency, spatially consistent. If two users are next to each other, how correlated are their channels? Across the array, and in deeper into the scene, like in the materials or regarding the objects in the scene. Of course, different tasks have different consistency requirements. Channel prediction, like we're going to see in the future, has a strong temporal requirement. And the question becomes, when do stochastic models can or cannot fulfill these consistency requirements? How does it reflect in the models that we're training? Are they still realistic or not? So for that, we selected two tasks, channel compression and channel prediction. And I'm going to introduce them quickly and then talk about their requirements. So channel compression, if you're not familiar, the goal is to reduce channel feedback overhead. So the user measures the channel, it's getting bigger and bigger, more frequencies, more antennas. And we often want to compress that for performing feedback to the base station, and the base station reconstructs the channel that the UV measured. So the input to this type of model would be, for example, 32 subcarriers and 32 antennas, and the output would be the reconstructed version of that. So very often we use the autoencoder type models for this sort of problem. This is channel compression, and this is one example of a model where the assumptions might be enough, because across frequency and across arrays, usually the CDL models are consistency in that regard. Regarding channel prediction, the second task, the goal is to estimate the future channel, because when we first measure the channel, it is usually a few slots before, a few milliseconds before we actually need it, and there's going to be some channel evolution that it's going to cause essentially some aging, some difference from when we actually need it. So if we are able to predict that, we have more beamforming gain, we have less outage, all the benefits of better channel estimates. So the requirements would be a proper progression across time of channel, and this means angle, delay, and Doppler coupled progressions. So for this type of model, we usually have a window of samples of the channel. For example, 10 samples every 1 millisecond. And here we actually keep single antenna and single subcarrier to focus 100% on the temporal evolution. And then we want to predict one channel further down the line, like 1 millisecond later, 5 milliseconds later. And in this case, we use a recurrent net just made of GRUs. This one is a popular one and simple one. All these models are available in our code. Regarding the sources of data, so the data where we're going to train these models on. Essentially, we have two sources, stochastic, the TDL, CDL, and UMA. Those are the three models we're going to focus on. We used Shione, but you could use the 5G toolbox. You could use NeoRadium, it also implements that. And map-based ray tracing. We use DeepMIMO, which is a database of pre-computed ray tracing scenarios. You could also use Shione ray tracing. But these are our two sources of data. And what is key to understand is we normalize them the same way. So it's not like we treat stochastic different than ray tracing. We normalize them the same. But the normalization depends on the task that we are focusing on. Particularly, for compression, we use zero mean unit variance. And for prediction, we simply divide by the maximum absolute value. These are typical normalizations for these tasks. And regarding the ray tracing scenarios we used one in ASU, one in New York, and one in LA from DeepMIMO. And at the bottom, you see some satellite images from them. And in the middle, some 3D models of those data sets. So in these 3D models, it's hard to see, but there are some blue dots. Those represent the base stations. And there are some red dots. Those would be the users. And the links between users and base stations would essentially consist of our channel traces. And the users, it's worth mentioning too, they have a uniform grid, so uniformly spaced, like 1 meter difference between each user in X and Y. And yeah, when we have multiple base stations, we just append each base station's channel to all the users. And there's a lot of ray tracing configurations. I'll be brief. What matters here is really the resolution. In channel compression, we don't need a lot of resolution because we are treating each sample the same. They are all going to end up in the same data set. But for channel prediction, the distance between samples matters because we're going to have sequences. And we assume a movement speed of a car, for example, at 10 meters per second. So if we want samples at every sample, and if we want to sample at, for example, 1 millisecond, then you do the math, it's going to end up at 10 millimeters. We need a ray tracing sample every 10 millimeters. So for this, we actually ray traced a variant of ASU every 10 centimeters. This took like more than a week to compute, by the way, but you can easily download it in DeepMIMO. And then on top of that, we interpolated on the path parameters, and then we computed the channel based on that. To be brief as well, we also only considered linear sequences, so only the same X and the same Y. I plotted all of them there, and these ended up being millions and millions of sequences. We ended up using only 200,000. And most of the parameters are very typical, 3.5 gigahertz, thousands of samples, more for channel prediction. The Doppler is only modeled for channel prediction as well, properly modeled in ray tracing, which is unusual and does require knowing angles of arrival and assuming directions. And mainly, we use the same performance metric, the same loss for both tasks, because we are always comparing channels. Either we compare channels between the original and the reconstructed in channel compression, or we compare channel between the true channel and the predicted channel in case of channel prediction. So NMSC is good enough and very good here. And lastly, just before we start showing the results, I'm going to show 3 results. One where we train and test on the same data set. One where we cross-test, so we train on one and we test on another different one. And another type of result where it's fine-tuning, where we train on one, pre-train on one, we fine-tune on a percentage of the target, and then we test on the remaining of the target. So these are often easy to visualize with equal-fusion matrices. So brace yourself.
Just to clarify, when you think cross-testing, that means, like, for example, one DeepMIMO data set with another DeepMIMO data set, or different portions of the same data set, or do you mean from CDL to ray tracing?
Wonderful question. It's exactly here. It's each data set. We have a number of samples per data set. So we cross-test across data sets, not, so in this case, across the columns, across the rows, we have where we trained, and across the columns we have where we tested. And here is, we always did, I think for compression, 50,000 samples was already relatively good enough. So what we care about here is the diagonal. This usually represents the in-domain. So when we train and test in the same data sets. And the conclusions here are brief. Essentially the CDL, the 2 CDLs we considered, the ray tracing, they have better performances here, suggesting, and we know that they are less diverse, that the full possible ranges of channels are more specific in these cases. So a model with the same degrees of freedom has has an easier job, has better performance in these cases. But in TDL and UMA, the performances, I'm seeing here the -6 NMSC dB. Those are harder and more diverse, and so they have a lower performance. Now, more interestingly, how they transfer. CDLs, there in blue, transfer very poorly to the ray tracing data sets. But the more diverse TDL and UMA models, they transfer relatively well. They already got a decent performance, and across the ray tracing data sets, the last one is ASU. We can also tell that ASU is a bit more complicated, which, well, having ray traced them, I know that ASU has way deeper non-line of sight, so it can be more diverse than the other two, which can justify this lower performance. Also, looking at that corner, it's quite interesting that ray tracing to ray tracing, they transfer relatively well already, without any fine-tuning. Now, when we fine-tune in that matrix there, based on the colors, by the way, we can look at purely the colors because the brighter the color, the better the performance. We see the two columns because those are when we test in CDL and UMA, those are difficult because they are very diverse. But we're more interested in that corner there where we fine-tune in ray tracing and when we test in ray tracing, and we see that we regained a lot of the performance. In this case, we fine-tune on just 1% of the available ray trace data, and all of them are essentially all below -10 dB. So in this case, it worked very well. So two quick conclusions. I don't have my clock, by the way. I'm running some production there. But two quick conclusions is we cannot use stochastic directly because what we saw across the diagonal is completely different than what we saw when we transferred. But stochastic is still useful because it definitely regained a lot of the performance gap. Now, to close the compression results, let us have a further look into how useful the pre-training actually is. So before, I only showed 1% fine-tuning. Now, let's look at when we have more data available. So when we have more samples available. And let's compare also to the model, not only the pre-trained models, which are the green and the red and the blue line, but also a model that didn't have any pre-training. So that was random weights. And we see that the more data we have, the better performance we will achieve. And we also see that the gap, the benefit of pre-training, is much larger the less data we have. Also intuitive. And beyond that, the benefit in ray tracing, using ray tracing data for pre-training, is the largest, followed by UMA and followed by CDL. And these gaps get smaller and smaller. So what I wanted to conclude here is pre-training is definitely valuable, especially when data is scarce. But beyond scarcity, especially when data is similar. And that's why the ray tracing data set, which we didn't even measure the similarity, maybe we can find even ray tracing data sets that are more similar to our target, but it already resulted in quite a good performance when we have a scarcity there. So last two results, channel prediction. Here we plot the horizon, the prediction horizon. Why making such beautiful slides when it's going to be stretched? Anyway, prediction horizon and performance. And here we only did TDL, CDL, and UMA, and the ASU. And the two pairs of lines, the top line is a simple sample and hold. So when we don't perform any prediction, when we just hold the channel, so this is essentially a baseline for channel aging. And the lines down below are what we actually get from the GRU model. So because they are lower, it means the GRU is doing something, is predicting something. But mainly what I wanted to direct your attention to is that the ASU model, the ray tracing model, is only very similar in performance to the stochastic models in essentially the very first sample for 1 millisecond horizons. And that can be associated with, for very short horizons, the Doppler is the main driver for change. Because in angle and delay, in 1 millisecond, you didn't change much. But as time goes on, as angle delay changes accumulate, then ray tracing gets different than the stochastic models. I can give you an explanation for why the curve looks like that, but what I mainly wanted to show here is that they look different already. And we are not even comparing models, we are just comparing the performance of the model. So when we start transferring them, we should expect some differences. And now we're going to go back to the confusion matrices for a particular horizon, for 5 milliseconds, typical prediction horizon. And across the diagonal, you're supposed to see the values that you see there. So around like 18, 16, and then for ray tracing, like -8. Yeah, that's what we see here. So to start, let's start with the transfer. Here, the in-domain doesn't matter much. We already saw in the previous one. For the transfer, stochastic to stochastic works incredibly well. And it's understandable because they are all modeling Doppler the same way. Well, rather, they are all modeling temporal evolution with Doppler. And it's with just Doppler, with just phase rotations, no angle delay. And that's why they transfer very well to each other. Now, when we try to transfer them to ray tracing, we see, ignore the second matrix, we see that they don't transfer at all. We have like positive, and MSE, it's a lot of error. But when we try to fine tune on 1% of data, like we did for compression, now some of them at least get negative. The performance gets slightly better, but still they fall very short of what we are getting from training in ASU directly. So in channel prediction, the conclusion is that definitely we need some more spatially consistent models, and the differences are much larger than in compression. So let me summarize our takeaways. Does stochastic provide realistic performance expectations? No. It gives relatively unreliable expectations, and we should always verify with a target that we are interested in. So if we want to deploy in the real world, it's worthwhile at least testing in ray tracing. But is stochastic still useful? And definitely it is. For tasks where the assumptions hold, the transfer was great. Sometimes with UMA and TDL, we even had good transfers without even even fine-tuning. But when tasks start not align, then it becomes a bit more nuanced. Depends on the amount of data, depends on the task itself. So the last two sentences, please let us as a community not rely only on stochastic anymore. Let us do the due diligence of at least testing in ray tracing. And we really at this point have no excuse because ray tracing has become extremely easy. Shiona has notebooks, MATLAB has notebooks. We have pre-ray traced scenarios in DeepMIMO that you can download and set running in minutes. So we definitely should use ray tracing as well, introduce it early in our data pipelines so that we don't have surprises at the end when things don't transfer. So that's all for me. Thank you very much. Wow. Yes, yes. Yeah, thank you. Exactly. So the question was whether this performance of cross-testing depends on the actual geometries of our ray tracing datasets. and it definitely does. Now note that we did not hand-pick these scenarios. It was really convenient selection. Like I'm familiar with ASU, and I picked the first two CD scenarios. So they were not hand-picked. And indeed, we could trace these performances back and perhaps compute some scene similarity metrics. And for sure, yeah, the channels are a function of the scene. So I agree with you. Yes, yes. Mhm.
So I have a comment and a question. So my question is for your channel prediction. I think if I remember your parameters correctly, I think your dropout was pretty high, right? For your GRU created channel.
You're asking about my dropout. It was probably quite high. Yeah, 0.5, yes.
So that just kind of so my question is, have you considered like maybe it's because then the result was that it did not transfer quite well. So my question is like maybe have you considered maybe it's like neural network specific? Like if you use like a more less biased networks, like I know everyone likes transformer these days. So like if you use like something like a transformer, would it generalize better?
Yeah, a great question. So I always have to repeat the question because I'm recording this. The question was, the GRU has a quite high dropout, which is related with having difficulties transferring. If we used another model, could it transfer better, like a transformer? And is the transferability a function of the model that we use? It definitely is a function of the model we use. In this case, I fine-tuned the whole model, and I let it train for long, and I also trained with different training rates. So I try to go around some of these dependencies with the model. By the way, it's worth mentioning that I picked these two models because they are fairly popular. Yeah, so to try to reduce a bit of the complexity with choosing a model, I just picked two relatively popular ones from literature. But you are completely right; it can depend on the model.
So I guess that kind of ties into my comment. I think like statistical models would be like great because you essentially have unlimited training samples.
What do you mean with statistical models?
Or like stochastic models. Like you
Well,
can easily generate a lot of training samples.
yes, yeah, but you are still training a model with that with that data. So note, by the way, that although this model did not transfer very well for ray tracing, it transferred perfectly in stochastic. So it's I don't think, and the performance was still good. So I think that this particular model did not have problems with transferring, but you're completely right, and I think we should test a few other models as well. Yeah.
But essentially, even if you have more data, so the data itself does not capture this angle delay consistency, right? So if the problem really needs this time of correlation, right, you really need this type of data as well. Right. One last question, maybe. Right.
The conclusion was really impressive. And my question is about the real measurement data. So can you expect the same thing to the real measurement data? For instance, you said that pre-training on the stochastic channel model would be beneficial to do something on the ray tracing, but is it the same to the real measurement data?
Great question. So we the whole time we used the proxy for the real world to be the ray tracing, and the question was, well, how about if we do the step all the way to the real world? Should we expect the same conclusions? Well, that depends on the bridge, on how similar the ray tracing is to the real world, first of all. Real world also has all sorts of imperfections that ray tracing doesn't. Hardware dependencies, we could list like 10 of them. I would expect that some, because it's still, we can look at just the machine learning field. this is purely transferring, learning transfer. So if we can't transfer to ray tracing, which is even better behaved than the real world, then we probably won't be very successful to the real world. So I think some of the conclusions do apply. Yeah, thank you.
All right, thank you. Thanks, Ron.
Thank you.
Right, with that we move to fourth paper, machine learning based more
Good luck.
directional beamforming with true time delay. Right.
Yeah. Thank you.
So I will ask you to.
How long was
transfer
this?
the delay.
Maybe not too long.
Take the end, so the professor also can take the full time.
Thank you.